Good morning to all of you. In previous session, we have seen causality and stability of LTI system in Z domain, which is characterized by its system function capital H of Z. Right. In today's session, we will be solving one example where we will be identifying the impulse response from the system function by using different causality and stability conditions. Right. So here the example has been specified where LTI system is characterized by its system function h of z. So h of z is given. So you have to identify the ROC of the h of z and you have to determine the h of n. That means you have to take the inverse z transform of this h of z to determine h of n. But for these three conditions, that is when system is stable, when it is causal and when it is anti-causal. So when we talk about stable system, so its ROC must include what? Unit circle. Okay, this thing we have discussed in the previous session. Okay, so its ROC must include unit circle. For causal system, ROC is exterior to circle and circle should have a finite radius, right? And when talking about anti-causal system, so it should be exactly opposite to the causal system, that is the ROC should be interior to circle, right? So these three conditions are there. But before utilizing these three conditions and identifying the inverse Z transform of h of z as h of n, we need to initially use the partial fraction expansion method to take the inverse Z transform of h of z, right? So the given system function h of z is that h of z is equals to 3 minus 4z inverse whole upon 1 minus 3.5 z inverse plus 1.5 z raised to the power minus 2, right? So here for performing partial fraction expansion, initially you need to avoid the negative powers of z, so you can rearrange these terms. So h of z is equals to, you can take z to the power minus 2 common from the denominator. So if you are taking z to the power minus 2 common from the denominator, so in bracket you will get z square minus 3.5 z plus 1.5. And if I am sending z to the power minus 2 from the denominator to the numerator, so it will be z square. So it will be 3z square minus 4z will be there, right? So I will simply write it down as, so z square 3 minus 4z inverse, right, whole upon, it will be z square minus 3.5z plus 1.5, right? So I'll just rewrite this last term or last expression. H of z is equals to what we have now. It is z square 3 minus 4z inverse 3 minus 4z inverse whole upon, let z square minus 3.5z plus 1.5. Okay, so again, for partial fraction expansion and to keep negative power of z in the denominator, I will send 1z on left hand side, so I can represent it h of z upon z, right, is equals to the remaining z from here I will multiply with bracket, so it will be 3z minus 4 will be there, right, whole upon z square minus 3.5z plus 1.5 will be there, right? Now I can factorize this denominator. I can identify the roots of it, right? It is a second order polynomial, so I can write it down as h of z upon z is equals to 3z minus 4 whole upon, the first root I can take it as z minus 0.5, right, and another z minus 3. Okay, so if you multiply these terms, so you will get these results. Okay, so if you are adding it, so 3 multiplied by 1 by 2 will be there, so it will be 1.5, and minus 0.5 minus 3 will be minus 3.5. So as per partial fraction expansion, I can write a upon z minus 0.5 plus b upon z minus 3. Okay, so again I can write it down as, if I'm sending this denominator on the right hand side, so it will be 3z minus 4 is equals to a into z minus 3 plus b into z minus 0.5, right? So if I'm sending these denominator terms here, so this z minus 0.5, z minus 0.5 will get cancelled, so z minus 3 in multiplication will be there with a, and with b, z minus 0.5 will be in multiplication. So to identify the value of a, so put what z is equals to 0.5 to get value of the value of a. Okay, so if I'm substituting z is equals to 0.5, right, so it will be 3 by 2 here, right, minus 4 is equals to a in bracket 0.5 minus 3, that is 1 by 2 minus 3, and this term will be 0, right? So if I'm evaluating this expression, so here 0.5 I can keep it as 3 by 2 minus 4, right, is equals to a, in 0.5 you can keep it as 1 by 2 minus 3, and this term will be 0 basically, right? So if I'm solving it, so it will be minus 5 by 2, right, is equals to, again here it will be minus 5 by 2a, right? So simply the value of a will be equals to 1. Okay, similarly you can find out the value of b. Okay, so to get value of b, you have to substitute z is equals to 3 in this equation. Okay, so put z is equals to 3 to get the value of b, constant b, right? So here if I'm substituting z is equals to 3, so it will be 9 minus 4, right? So it will be 5 is equals to, this 3 minus 3 will be 0, so this term will be 0, and b into 3 minus, is that 1 by 2 will be there, right? Correct. So it will be 5 by 2. So 5 is equals to 5 by 2b, right? So b will be equals to, simply b is equals to 2. So these are the values for a and b. Okay, so we can substitute these values, a is equals to 1 and b is equals to 2 in this partial fraction expansion form. So you can write h of z upon z is equals to, h of z upon z is equals to 1 upon z minus 0.5, 1 upon z minus 0.5, right, plus in place of b 2 upon what is it, z minus 3. Now I can set this z on the right hand side, right? So I'll get h of z is equals to z upon z minus 0.5 plus 2z upon z minus 3. I'll set this z in denominator, so I'll get h of z is equals to 1 upon 1 minus 0.5 z inverse plus 2 upon 1 minus 3z inverse, right? So this is what is the required partial fraction expansion. Okay, so now depending on those given three conditions, right, is the first condition in the example, so the system is stable, right? So for first condition we can write here, initially I will just rewrite this equation that we have identified after partial fraction expansion. We already discussed the inverse Z transform, where we have seen three methods, that is contour integral, power series expansion, which is identified by using long division method, and last one was the partial fraction expansion, that is table lookup method. So here we are using this partial fraction expansion to get the inverse Z transform h of n of capital H of Z. Right, so here we have 1 upon 1 minus, what is that, 0.5 Z inverse, right? And second term is plus 2 upon 1 minus 3 Z inverse. So as per this expression, the H of Z has two poles at Z is equals to 0.5. If I'm substituting Z is equals to 0.5, so this 0.5, 1 upon 0.5 will get cancelled, so 1 minus 1 will be 0, 1 upon 0 will be infinity. So one pole will be at Z is equals to 0.5 and second pole will be at Z is equals to 3, right? So if I'm substituting 3, Z is equals to 3, so it will be 1 upon 3, 3 will get cancelled, so 1 minus 1 will be 0, 2 upon 0 will be infinity. So it has two poles, one at Z is equals to 0.5 and second will be at Z is equals to 3, right? So as per the given conditions, as per the first condition, since the system is stable, its ROC must include the unit circle, right? Its ROC must include the unit circle. So therefore, and hence it is, that is ROC, as there are two values of poles, so 0.5 and 3, right? So the ROC should contain the unit circle, so ROC must be greater than 0.5 but it should be less than 3, right? So it contains the unit circle, that is the value of Z is equals to 1. Okay, so here this mod Z is greater than 0.5 but it is less than 3. And when we have seen partial fraction expansion, so if you have terms in this form, that is you are identifying the Z inverse of 1 upon 1 minus pk Z inverse, so its Z inverse can be pk raised to the power n u of n if ROC is exterior resolver, that is mod Z, ROC conditions are mod Z greater than pk, right? And second was minus pk raised to the power n u of minus n minus 1 when mod Z is less than pk, right? So this standard form of partial fraction expansion we already discussed when we have seen the inverse transform by partial fraction expansion. So if you observe these ROC conditions here, so for first term, as mod Z is greater than 0.5, so this first form will be utilized, and for second term, as mod Z is less than 3, so it is less than pole value, so this second term will be utilized. So as per this condition, you can directly write down the h of n. Okay, h of n will be non-causal in this case, right? But system is stable here. Okay, but the system is non-causal as well, right? So h of n will be simply, h of n will be equals to what? Here it is 0.5 raised to the power n, that is 0.5 raised to the power n into u of n for the first term, right? Because mod z is greater than 0.5, it is greater than the pole value, so therefore pk raised to the power n u of n were written. But for second term, as the value is the ROC value is less than the pole value, that is mod z is less than 3. So therefore you can write this, you can utilize this second form. So this 2 is constant here, so this minus sign will be there, so minus 2 into the pole value is 3 here, so 3 raised to the power n into u of minus n minus 1 will be there. So this will be the impulse response in first condition, that is when system is stable, and this will be the its ROC, right, when system is stable, correct. Similarly for second condition, what is the second condition? The system is causal. So when it is causal, so it should be the exterior of circle. Again I will write this h of z is equals to, what is that, 1 upon 1 minus 0.5 z inverse plus 2 upon 1 minus 3 z inverse is there, right? And it has two poles, z is equals to 0.5, z is equals to 3, right? And as system is stable, system is causal, the ROC will be mod z greater than 3. Okay, it should be greater than 0.5 as well as it should be greater than 3, right? Because it will be exterior to circle. Okay, so again as per this condition what we have specified, as it is greater than 3 both cases, so this first form will be utilized to write down the h of n. So h of n you can specify it as h of n is equals to 0.5 raised to the power n into u of n plus 2 into 3 raised to the power n into u of n, right? So this will be the impulse response when system is causal and its ROC will be exterior to circle, right? Mod z greater than 3. As per third condition, so what is third condition? System is anti-causal. Okay, system is anti-causal, so ROC will be interior to circle. The system is anti-causal, right? The ROC will be exterior to circle, so sorry, interior to circle in case of anti-causal. In case of causal it was exterior. In case of anti-causal it will be interior to circle. So again h of z will be this one. Okay, it has two pole value 0.5 and 3, right? So ROC will be interior to circle, so it should be mod z less than 0.5, right? So as this ROC value, that is mod z, is less than both pole values, so as it is less than both pole values, so second form will be applicable here. So here I can write h of n directly as h of n is equals to minus 0.5 raised to the power n into u of minus n minus 1. Again here minus sign will be there, so minus 2 3 raised to the power n u of minus n minus 1 will be there, right? So here you can take minus sign and u of minus n minus 1 common if required, or you can keep this as it is. Okay, so this is the required impulse response, okay, when system is anti-causal and its ROC will be interior to circle. Okay, that is mod z is less than 0.5. So this is how you are utilizing the stability and causality conditions defined by using system function to identify the impulse response by specifying its ROC. Okay, so ROC includes unit circle, or it may be exterior to circle, or it may be interior to circle, depending on whether system is stable, causal, or anti-causal. Okay, so initially we have applied partial fraction expansion to get this particular form where we can directly apply the inverse Z transform to these terms, but inverse Z transform are identified by using the ROC condition depending on whether the system is stable, or causal, or anti-causal, right? So in next session we will be discussing the pole zero cancellations, right? So the topic that is pole through cancellation topic we'll be discussing in the next session. Thank you for joining this session.